Assalamualaikum warahmatullahi wabarakatuh. Welcome to the fifth video lesson for your physics online learning. We are still in chapter 26 of radioactivity and atomic physics. So for this lesson, we're going to look at uses of radioactivity. Now, radioactivity, like I said, can be harmful to the body, but humans have found ways to use radioactivity to our advantage in our daily lives and also in the industries and in particular in medicine. So we're going to look at that today for this video lesson. These are the learning objectives for this video lesson. Learning objective number 1 is to discuss the way in which the type of radiation emitted and the half-life determine the use for the material. So depending on the type of radiation, alpha, beta, or gamma, and also its half-life, there are specific uses to these type of radiation. And we're going to look at that for this video lesson. The second lesson objective is we're going to look at something that's called carbon dating. And at the end of this video lesson, you should know how carbon dating is used using carbon 14, so which is this thing here. So that's carbon 14. Right, so let's start. Carbon dating. What is carbon dating? It's a technique that paleontologists use in order to figure out how old a fossil is. So you can see these two pictures here. This is sort of like a fossil of a tree, of a plant, and this is a fossil of a dinosaur, I think, or a lizard. And you can check the amount of carbon 14 inside that fossil or inside that bone, and you can do some calculations to figure out how old that fossil is. So that is what is basically what carbon dating is. Now carbon is made of the isotopes carbon-12, 13, and carbon-14. And out of these three isotopes, carbon-14 is radioactive. It has, we know it has a half-life of 5,700 years. Carbon-14 is present in carbon dioxide, which living trees use in photosynthesis. After a tree dies, it cannot take in any more carbon-14, so the carbon-14 that is already present in the tree will slowly decay. The amount of carbon-12, however, will not change. So for carbon dating, we are only looking at, so we have a lot of carbon in our body. So a lot of living things are made of carbon. And when we die, carbon-14 especially will start to decrease inside our body. When we are living, the amount of carbon-14 in our body is constant because we always take in carbon and it fills up the amount of carbon-14 in our body. But once we die, that amount will slowly decrease, and we can look at how much it decreased and figure out how long time has passed since we died. So the ratio of carbon-14 left in the wood to the amount of carbon-14 in living trees can be used to tell us the age of the wood. So we can, like I said, we can compare the amount of carbon in living things of the same type, and then the amount of carbon inside the fossil or the dead specimen, and we can use that and calculate how much time has passed since it died. Animals also take in carbon-14 in their food while they are still alive. After their death, the proportion of carbon-14 in their bones can tell us how long it is since they died. Okay, so like I said, once they die, the amount of carbon-14 is slowly decreasing, and we can use that information to figure out how long has it been since they died. Okay, so here I have a simulation that shows how carbon-14 is done. We're going to look at a tree, and then it will die in this simulation, and then we're going to look at the amount of carbon-14 in that tree. Okay, just to give you an example. So here I have a graph of the amount of carbon-14 remaining, so you can have a look at this graph while the tree is dying as time passes. Okay, so let's start and see what happens. So that's the tree. It's still living, and then it died. So take a look at this graph here. So once it died, the amount of carbon-14 will slowly decrease as time passes. So now we're at 4,000 years already. Okay, and the carbon-14 is decreasing in a way that it follows a decay curve. So it's a curve as it decreases. Okay, so that's sort of what happens to carbon-14 when things are dead. Let's do some calculations in example 4 and see how carbon dating is done. Okay, I'll read the question out for you. A bone found is said to be from a king that died more than 15,000 years ago. So they found a bone that they said has died more than 15,000 years ago. After some investigation, it was found that there is still 25% of the original carbon-14 left in the bones. Given that the half-life of the carbon is 5,700 years, is the bone really of a person who died more than 15,000 years ago? So they found this bone from a king, and they said this bone must be 15,000 years old. And now we have to do a bit of calculations to check whether that's true or not, whether it is really 15,000 years or maybe less or maybe more. So let's do that calculation using half-life. So we know the half-life of carbon-14 is 5,700 years. And then there's 25% of the original carbon-14 left. And we want to, those are the two key pieces of information that we will need in order to do this calculation. Okay, so like half-life calculations before, we need to have some sort of timeline. So let's just do a timeline of carbon, the amount of carbon-14, and also against time. Okay, so that's the timeline that we are doing for this example. In the beginning, when the king initially died, the amount of carbon-14 inside his body is still 100%. Okay, 100% of the carbon-14 still exists. Let's say the time, then that's the start of, that's when he died. So time is 0. And then after, remember, the half-life of carbon-14 is 5,700 years. So after 5,700 years, the amount of carbon-14 now should be half, so it should be 50%. Okay? And then after another 5,700 years, so plus another 5,700 years, so that's 1,400 years. Now the carbon-14 is halved again, so half of 50%, that's 25%. And you know what? That 25% is the amount of original carbon-14 left currently. Okay, so that means we're gonna stop there, and that is our answer here. So how much time has passed since the king died? The amount of time is this one here. Okay, so that's our answer. Let's just write that down. So answer, the king died 11,400 years ago and not 15,000 years ago as was stated. So whoever said the king died 15,000 years ago is not true. After our calculation, we figured out the king actually died 11,400 years ago. Okay, so that's how we use carbon dating to calculate how long time has passed or the age of a certain bone or fossil. Radiation is mostly often used in medicine and industry. So we're going to look at the medicine sector first, and we're going to look at how radiation is used in medicine. The first use is we can use radiation to kill cancerous cells. Cobalt-60 and cesium-137 are often used for this purpose. They emit gamma rays. The dose of radiation must be carefully calculated to destroy cancerous tissues and leave healthy ones alone. So you can see in this picture here, this is how they actually kill cancerous cells. There are several emitters of gamma rays, and each of these emitters emit very weak gamma rays. But as you can see, they all intersect at one point in the body. The effects of each of these gamma rays will all add up and combine to have a stronger effect at that point there. So on its own, one gamma ray is not strong enough to kill the cancerous rays, but together, by intersecting all of these rays, it can be strong enough to kill cancerous cells at a certain point in the body. So this is how they actually do it. Why do we use a gamma emitter? Why don't we use an alpha or a beta emitter? And the answer to that is actually quite straightforward, because out of these three radiation types, gamma rays are the strongest when it comes to penetrating power. That means it can pass through the body. And gamma rays, when it hits a cell, it can heat up the cell. Okay, it can heat up things. That's why we use gamma rays. The second use of radiation in medicine is that you can use radiation to destroy bacteria on medical instruments. So it's much more convenient and efficient than boiling. So in other words, you can use radiation to sterilize medical instruments. The third use is to find out if the thyroid gland in the body is working properly. So to do this, a patient is given food containing iodine 131, and iodine 131 is a beta emitter. The radioactive iodine can be detected as it passes through the body, okay, because it's a beta emitter, so it passes through, it can only be stopped by aluminum, and it passes through the body quite easily. The half-life of iodine is 8 days. Hence, in 2 weeks, there will be a few traces left. So another reason why we use iodine 131 is that it has a short half-life. So a short half-life means that it will decay quite quickly and disappear quite quickly, so that it won't cause harm to the body. Now we're going to look at the use of radioactivity in the industrial sector. So the first use is in the production of metal foils or even paper. Radioactive materials are used to make sure the thickness of a roll of metal sheet or paper is consistent throughout. So we can use radioactivity to check the thickness of a piece of metal, a sheet of metal or paper or whatever it is, and make sure it's uniformly, the thickness is uniform. So in the diagram, the detector measures the amount of radiation passing through the paper. If the paper is too thick, the detector reading drops. The detector then sends a message to the rollers, which will vary their distances to make the paper thinner. So let me explain how this is done. Right, so here I have a simple diagram of the industrial roller. So in this case, we have a few rollers here. These are the black circles that I've drawn. And then you have a green piece of sheet here. That is, let's say that's the paper. Okay, so this industrial roller is trying to smoothen out and make sure the paper is at a certain thickness. And we have this pink here, pink object here, that's the emitter, and this yellow object here, that's the detector. So the emitter will emit radiation, and the radiation will pass through the paper, okay? And let's say at a thickness of, so let me just write something here. Let's say at a thickness of 10 millimeters, the detector detects a radiation of, let's say, 1000 counts. Okay, for example. Okay, this is when you want the paper to be 10 millimeters thick, and then so how do you know it's 10 millimeters? You check the radiation. In this case, the radiation that passes through is about 10,000 counts. Now, let's say there's something wrong with the manufacturing process, and then it turns out the paper is being rolled out thinner than what you want it to be. So instead of 10, oops, so instead of 10 millimeters, now the paper becomes, let's say, 8 millimeters now, right? So because the thickness of the paper is thinner, the radiation count will increase because a lot more radiation is passing through because it's thinner. So it's very easy for the radiation to pass through. So let's say the count becomes 2000. Now, when the count so the system knows that the radiation count should be 1000, but once the system detects that, oh, there's a lot more radiation than normal, so that means the paper must be thinner. So the system will detect that and will correct that and will roll the paper to make sure it's much more thicker. Okay. So let's say the paper is a lot more. Okay. So that's in the case of when the paper is thinner than normal. If the paper is, again, if there is something wrong with the system and the paper is thicker than normal, let's say it's 20 millimeters now, so that means the radiation count will drop because a thicker paper means that a lot less radiation will pass through, so it's harder. So a lot more radiation is absorbed by the paper and not a lot of radiation is passed through, so your radiation count will drop. And again, the system of this industrial roller, the computers or whatever, will detect this and will then try to correct and give the correct amount of thickness. Okay, so that's how we use radiation in this case. So for the industrial roller, would you use an alpha source, beta source, or a gamma source? Not alpha because it has a weak penetrating power. It will not pass through, especially it will not pass through paper, let alone metal. Not gamma because it is too penetrating. So no matter what the thickness of the paper is or the thickness of the metal sheet that is being produced, it will be unaffected by the thickness of the paper. So whether it's thinner or thicker, it's unaffected. It will just pass through and the system cannot detect that. For this specific purpose, we use beta source because it is strong enough to pass through, but would still be affected by the thickness of the paper. So we use gamma source. The second use of radioactivity in industries is to detect leaking pipes. So as you can see here in this picture. So to do this, a small amount of radioisotopes is injected into the pipe. It is then detected by a GM counter above the ground. The most common tracer is called technetium-99, and it is very safe because it only emits gamma rays and do not cause a lot of ionization. Now, why do we use gamma rays in this case? Can you figure it out? We use gamma rays because gamma rays is very strong when it comes to penetration, and it has to pass through the ground and reach to above the ground. And gamma rays are is the best when it comes to that. We also use radioactivity in food industries. So let's look at that now. Food spoilage is a serious problem. The major cause is bacteria, molds, and yeast which grow on food. Irradiation of food with gamma rays will kill 99% of the disease-carrying organisms. This treatment is not suitable for all foods. So some people fear that the irradiated food are radioactive. In fact, foods contain a small amount of natural low level of radioactivity, and the treatment simply increases it slightly. So basically, before food and beverage industries package the food, some of the food they would just shoot radiation to it in order to kill the bacteria before they package the food inside the tin or inside the container or whatever. Okay, and then there are some people that are worried because they are giving radiation to the food or shooting these gamma rays to the food. It will make the food radioactive, but not not so because it's harmless radiation. The dose of radiation is carefully calculated. By the time the food is eaten, the extra radioactivity would have been decayed. And that's the end of the lesson. So we looked at the uses of radioactivity in three sectors: in paleontology, so that's carbon dating. We use carbon-14 to figure out the age of something, and especially fossils. And then we looked at uses of radioactivity in industries. So in industries, we use radioactivity in industrial rollers and also to detect any leaks in pipes, especially underground. We looked at uses of radioactivity in medicine. So we use radioactivity to kill cancer, to sterilize medical equipment, and also to detect if there's something wrong with our organ, especially the thyroid gland. So those are the things that we looked at for this lesson. And I'm going to stop there for today. So next week, we're going to look at the hazards of radioactivity and also how we can handle radioactivity so that we can safely use it. Okay, until then, stay safe. Assalamualaikum warahmatullahi wabarakatuh, and thank you for watching.